You're listening to the Common Descent Podcast. Hello, David.
Hello, Will.
Hello, listeners.
Hi, listeners.
And today, we welcome you back to the Common Descent Podcast as usual. And with today's episode, we are going to talk about something. This is a very interesting one called the Ediacaran Biota.
Yes, this came up a while ago.
Indeed. So you as we are with the MCU movies, we are finally making good on a brief teaser we made in a much earlier episode.
Yes. Yes, 21 episodes ago or something.
See, I mean, and so we're even farther back, number of things wise than Marvel was. So really,
Take that.
Yeah. We are referring back to our Cambrian Explosion episode because we mentioned this suggested episode there because these subjects are tied together.
Yes.
Because the Ediacaran Biota is a very unusual group of organisms that appeared on Earth right before and lasted right up until the Cambrian Explosion.
Yes, this was the appearance of multicellular creatures before the famous appearance of multicellular creatures.
Yeah, it's a weird one, and we're going to get into it.
Mm-hmm.
Today's episode, as we mentioned, was suggested to us by one of our listeners over Gmail, and this was requested by Samuel.
Thank you, Samuel.
Thanks. I've been looking forward to this one. It was a very interesting one to do, so we hope you enjoy it. But before we can give you the episode you asked for, we have announcements.
Yes, just a few.
Very brief, and most of them have to do with other listeners because we got some new patrons.
Yeah, if you are a patron of a certain level, we will say your name on the podcast.
Indeed. And we got 3 of those since last episode, so we've got a few names to say. So thank you, Lydia Jorgensen, Andrew Brady, and Anna Sampson.
Thanks, guys. We really appreciate it. We say thank you to the patrons all the time and how much they mean to us, and it is always true. Huge thanks to Lydia, Andrew, and Anna for joining us.
Indeed. I know one of these, and so thank you all the more to everyone who's listening as well. I was not prepared for us to have 3 names this episode.
Yeah.
Speaking of cool listener stuff, we wanted to also re-mention that there is actually a survey on our Facebook page and Twitter that is specifically for you, our listeners, to make your voices heard.
Yes, that went up a little while ago as of this recording, and we have already gotten a ton of great responses.
Really cool responses.
Thank you to everyone who has responded. We're going to leave it up until the very end of the month. So it'll be a week after this episode comes out. The survey will still be up. So if you haven't seen it, it's pinned to the Twitter. It's pinned to Facebook. We'll also put a link in the description for this podcast episode.
Absolutely.
And we'll put it on the blog. This link will be everywhere, so you can take a look and let us know what you think and what you would like to see in the Common Descent podcast.
Yeah, you listen to us all the time. We want to listen to you.
Indeed.
On a similar note, but not happening quite yet, so when it comes to surveys, we also want to hear your opinion on another issue.
we did this once before.
Yes, we asked your opinion once, but now there are more of you. And we would like to hear all of your opinions and some of your opinions again. And it has actually been mentioned. So we are indeed going to bring back our opinion poll on which is the superior animal, crocs or snakes.
Yes, we did this way back after episode 3.
Mm-hmm.
And some people have been asking about it. So, yes, we're not going to say too much about it now, but stay tuned for some notes. The poll is coming back.
It'll be, keep your eyes open. Be ready to make the correct choice.
Some animals always have their eyes open because they're awesome like that. Just saying. Some of the best animals.
Some animals actually have more than enough eyelids. So
some animals have like extra modified eyes for seeing infrared light. Hey, let's talk about the news.
So on to our news. As usual, every episode we cover some recent science news, typically paleo, to keep us and you all up to date with what's happening in the science world. And David, if you would like, take it away.
I certainly will. This first news piece that I have brought today is about pterosaurs, because there is not enough pterosaur talk on the Common Descent podcast.
This is true.
Pterosaurs are, of course, the famous flying reptiles from the age of dinosaurs. Pterosaurs lasted throughout the entirety of the Jurassic and Cretaceous periods, and before that, they disappeared during the mass extinction at the end of the Cretaceous, along with most of the other dinosaurs. But an interesting thing that has come up in people's research of pterosaurs is that there seem to be less pterosaurs, a lower diversity, right up toward the end of the Cretaceous, which has left some people wondering if the pterosaurs were struggling for a while leading up to the mass extinction, if they were sort of on their way out in some ways. However, a new study has reported on a new fossil site that has shown us that pterosaurs at the very end of the Cretaceous were actually doing quite a bit better than we thought they were.
Cool.
This is a study by Nick Longrich et al. In PLOS Biology. These new discoveries come from a couple of phosphate mines in Morocco. This is the late Maastrichtian, which is the very end of the Cretaceous. Before this, all the pterosaurs known from the end of the Cretaceous are one family of pterosaurs, known as the Azhdarchids. But in this fossil deposit, they found over 200 fossil specimens representing 6 new species and 1 already known species.
Wow.
In 3 different families. There are Azhdarchid pterosaurs, pteranodonted pterosaur remains, and nyctosaurid remains, which is really cool because it means that there was a much higher diversity of pterosaurs right up at the end than our other fossil remains have indicated. This is not only the largest collection of pterosaurs from this time period, and the pterosaurs themselves range from wingspans generally 3 to 6 meters. So we're looking at 10 to 20 foot wingspans. There are remains at the site. One of the species that they found appears to have been one of the giant pterosaurs with wingspans up to perhaps 9 meters. So, wow. Yeah, no, huge. So not only does this suggest that there was more of a diversity, right? We've got multiple families of pterosaurs surviving right up to the end of the Cretaceous, which is to say that they weren't in decline as, or at least certainly not as much as people had suggested, but they also looked at what's called functional diversity. So when you're looking at functional diversity, you're basically saying let's look at diet, feeding mode, locomotion, body size, habitat, all the sort of the niche. How many niches are these animals filling? And when they compared functional diversity at this site, other sites of this time, sites a little bit earlier, they found that functional diversity was not decreasing toward the end of the Cretaceous, and their results actually found it increasing slightly.
Interesting.
Which suggests that pterosaurs were not only doing quite well toward the end of the Cretaceous, but were still dominant in their ecosystems, occupying many different niches, still the biggest flying things around. So this tells us a little bit more about how pterosaurs were doing, raises the question, as with all the other creatures, of why they went extinct so dramatically at the very end of the Cretaceous, and raises the possibility that there are other pterosaur families that survived longer than we thought they did, and we just haven't found their fossils yet.
Very cool.
Which is especially possible with pterosaurs because they're very delicate and they don't fossilize very well.
No, they're extremely rare because of just everything working against them. Aren't most typically fossilized in marine environments after dying probably at sea. So it's one of those where they may also typically be living in places that don't want them to fossilize. So,
Yep. This actually ties into a principle in paleontology called the Signor Lips effect, which is that essentially fossil animals always look like they go extinct before they did,
yeah.
because the odds of the last one fossilizing are extremely low. So these authors are saying that our evidence of pterosaurs in decline might just be because we're missing the fossils.
Yeah, well, it's the mentality of why you can never prove a negative is I can
Yep.
never find all the spots this rare turtle could be hiding to confirm that it's not in this environment, because there could always be that one that I'm just not finding because there's only one.
Yeah.
So,
And that becomes likely when you're trying to pinpoint the very last moment of a group's existence.
yeah,
So hopefully there's more pterosaurs out there.
that's very cool, and I find it interesting because it's a neat answer, but also does not give us further answer to the bigger question. So it's cool that they were doing well, but also one of those where it's like, well, then what were you doing? Which I kind of always enjoy those moments.
Absolutely.
Very cool. Now, my first news article is a very interesting one because it deals with a unique feature in reptiles. This is a early case of the tail loss ability in an ancient group of reptiles separate from modern lizards.
Ooh.
Yeah. So, as many of you probably already know, many lizards nowadays have the ability to either allow their tail to break or detach when attacked by a predator. And often the tail will even continue to wiggle to act as a distraction, to give them a chance to get away whilst being attacked. This research deals with an ancient group of reptiles that seems to show signs of the same behavior or trait. And as I mentioned, separate from the lizards one, which is very cool. These reptiles are known as captorhinids, sometimes also known as cotylosaurs. And they were a very old, small to fairly large. The largest ones were about 2 meters long, so, just over 6 foot.
Yeah, iguana-sized.
Yeah. So these were reptiles, very lizard-like in their overall design. They had 4 limbs. They were pretty squat to the ground. You found them in the Carboniferous up to the end of the Permian. This would be between 300, 255 million years ago. And they're extremely successful. They were globally found across Pangaea. During the late Permian is really when they were showing their success. And classically, they have very triangular shaped heads with kind of a hooked snout, like a downturned front of their upper jaw.
Yeah.
So, very recognizable reptile shape. LeBlanc et al. Published in Scientific Reports 8 recently that when studying some of these specimens, they noticed in the tail vertebrae little cracks through the middle that are reminiscent of the tail loss vertebrae in modern lizards.
Yeah, sort of intentional planes of weakness.
Yeah, exactly. Like a purposeful. It was like in a car where parts are meant to bend or break when in a wreck. It's a purposeful breaking point.
Yep.
Actually down the center of the vertebrae.
Yep.
So these small cracks were found by looking at more than 70 tail vertebrae from both juveniles and adults of fossil specimens.
Okay.
They were able to confirm that these were natural features, not accidental cracks due to fossilization.
Right.
And they were comparable to the modern lizard vertebrae. So it's all signs are pointing to that these reptiles also had this tail loss feature. And it would make sense as to one of the reasons why they may have become so successful if they were the, so far as we can see, only reptile that had this special ability.
Yeah.
And is even more interesting to the fact that this means that this trait was evolved and then lost and then re-evolved by lizards 70 million years ago. So way after.
Yeah, this is interesting because these are Permian creatures,
Mm-hmm.
which is before the age of dinosaurs showed up, way
Yep.
before lizards showed up. This is a very ancient group of reptiles. So the fact that this trait had already evolved back then is really cool to see it showing up in a much earlier group of animals using this feature the same way
Yeah. It's
that lizards have recently.
a very unique form of convergent evolution, which
Yes.
is cool. Now, one of the other interesting things they noticed, which I thought was very cool, is they actually noticed a difference between the juveniles and adults on the cracks in the tail. When they looked at the juveniles, the cracks were more pronounced and more substantial. While they looked at the adults, they seemed to be a little more fused, or less weak,
Interesting.
which could suggest that as they grew, they lost the need to evade predators as much. When small,
Yeah.
young cotylosaurs, they need this ability to escape, and then once they get bigger, they stop needing to run away as much.
Interesting.
Yeah.
That's a very cool finding.
Mm-hmm.
It's incredible. Always incredible what sort of things we're able to figure out about fossil creatures.
Mm-hmm. I like these things because they always remind me, and hopefully us as a group, that animals have been complex for a very long time,
Yes.
and they've been doing cool tactical behaviors to survive way longer than we often give them credit for.
Absolutely. My second news piece has to do with two things that we don't talk very often about. One is modern creature news, and the other is bugs.
Gasp.
This is a study about spiders in Hawaii and a very interesting trend in the way they have evolved as they've spread through the islands. So this is a study by Rosemary Gillespie et al. In Current Biology. They were looking at a particular group of spiders called stick spiders. These are very slow moving. They have these long abdomens, so their bodies are kind of long and stick-like. They were the article that I read referred to them as the sloths of the spider world. Very slow, but they're predators like all spiders. And what's really interesting is that as you hop between the islands of Hawaii, the big four islands, right? Kauai, Oahu, Molokai, Hawaii, you see over and over again 3 color variations in the spiders.
Mm-hmm.
Gold, which camouflage against the underside of the leaves. Dark brown, which camouflage against rocks and bark. And white, which camouflage against lichens.
Cool.
And this study was basically looking at how have they evolved, right? What are the relationships between these groups of spiders? And you might expect that a group of white spiders spread from island to island, and a group of brown spiders spread, and a group of gold spiders spread from island to island. But that's not what they found. What they found was that the spiders on each island were more closely related to each other than they were to the spiders on the other islands, which suggests that these spiders dispersed to the islands, and every time they went to the islands, they re-evolved gold, white, and brown variants.
Nice.
Which is really an interesting finding.
Mm-hmm.
Because that raises all sorts of questions, such as, why are you continuously evolving those same 3 colors? What are the limitations there? There's a long-standing question in evolution. If you rewound the tape, would you get the same stuff?
Yeah.
If you reset the Earth to 60 million years ago and ran it again, would you get all the same creatures?
Mm-hmm.
In this particular case, we're kind of seeing that. The same things have evolved over and over again.
Take that, chaos theory.
Now, this has not only been seen in these spiders. There's another group of spiders called the long-jawed goblin spiders, which have a similar thing throughout the Hawaiian Islands. A similar thing has also been seen with anoles, which are lizards in the Greater Antilles, where they've evolved certain types of lifestyles over and over again on each island. In this case, the authors suspect that there might be there's two ways that they might explain this, and they don't have to be mutually exclusive. One is that these are the only easy ways for the spiders to live. That living on the bark, living on the lichens, living underneath the leaves, those are the three best ways to be a spider on a Hawaiian island, to be a twig spider. Mm-hmm. So they constantly fall into those niches over and over again. Another explanation might be that it is a physical limitation. And they described how the color variation is really just a change in certain molecules on the skin or on the outer layer of the body, and how those molecules interact with the pigments. So it could be that they haven't come across a change that would allow for a different variation outside of those three color variations. But what's really interesting, the other, of course, thing that's really interesting is that while this pattern has been seen in at least two groups of spiders and at least one group of lizards, there's tons of spiders and lizards that we don't see this with. So this is something that is happening to this group of spiders and a couple of other groups, which suggests that either based on their environment or based on their physical mutability, they are limited in what they are capable of doing in these niches, which is just one of the coolest things you could find. I think that's really, really fascinating.
No, that's really cool. The thing I really like about that is the fact that you typically think that it's completely random mutations, but it's often easy to forget, or sometimes you come across times where it's like, yes, any mutation could happen, but this mutation's real easy.
Yeah.
So it just keeps happening. And so it allows them to evolve in similar ways. I also really like the mental image of the spiders being on an island and be like, look at us, we're so clever. Those other island spiders, they got no clue how to live.
we came up with 3 different colors.
Yeah. Oh man, when we have our annual meeting, they're gonna be so impressed.
Oh man.
That's very cool. Now, my last one has a similar thread in that it deals with partially modern groups. And if I forced everyone to make a guess as to what group it dealt with, you'd never get it. This is a report about alligators versus crocodiles.
So moving on to our main discussion topic for the episode.
This is important. This is important. You all need to hear this. This is a recent study that looked at limb measurement in specifically crocodiloids and alligatoroids, which it would include alligators and caimans in their group and all crocs in theirs, and found an interesting trend in many of the modern groups as well as a few fossil specimens. So this research was done by Ijima et al. And it was published in the Royal Society Open Science. Whilst looking at specimens, he did a number of measurements, but noticed the trend in the front and back limbs, specifically the humerus and femur.
Yeah, the upper arm and upper leg bones.
Yep, the main ones, the big ones. What they call in the paper the stylopodia bones.
Yep.
I learned that term while reading this.
Each section of our limbs has a name.
Yes, it does.
The humerus and the femur are both the stylopodium, and the radius ulna and the tibia fibula are one of the other ones. I don't remember
the other term.
Yes. I always forget which ones are which, but yeah. Each piece has a name.
This is the first time I came across that, which is neat.
Yeah.
But they found
Zygapodium, I believe. The Zygopodia.
There you go.
I think that's what they are.
They found that the trend is that alligators have shorter femurs and humeri than crocodiles.
Interesting.
Which is very interesting. The first thing that this might shed light on is a very interesting thing that I actually learned about at my first visit to SVP. We talked a little bit about it in the Crocs episode, but many modern day crocodilians gallop when scared.
Right.
When trying to escape. Famously, the freshwater Australian crocodile and the Cuban crocodile are the only ones that typically do it when they're full grown.
Mm-hmm.
The Cuban crocodile does it towards stuff because they're awesome.
Yeah.
So they're
it's
just
coming right at us.
Yep. It literally chase you around its habitat. I have watched videos of it. It's wonderful. But one of the talks I saw at SVP was looking at the galloping mechanics, and they found that lots of crocodiles do this as juveniles. Like when they're young, many baby crocodiles gallop when pushed to have to get away quickly or to move quickly. Yeah. Alligators don't.
Interesting.
And at that time when they looked, they couldn't see anything that stopped alligators directly from doing it, but alligators just wouldn't gallop.
Interesting.
This could point to a potential reason why that behavior never really developed in alligators. This included 20 of the modern species, so almost all of them. They're only missing a handful at that point.
Everybody not named Temistoma.
Yes. They did include the gharial as well, and I think they were only missing actually, I think they did include Temistoma. They were only missing a few of the crocs.
Okay.
They had almost all the caimans. They had both alligators. So they had huge variety for modern and a few extinct members on both sides. Okay. In total, they had 120 crocodilian skeletons that they measured for this. Yeah. So it was a good selection. And the reason this is a significant find is though alligators and crocodiles seem very, very similar in their morphology, in their overall shape and physical layout, they split evolutionarily 80 million years ago.
Yeah.
So they have, even though they've stayed very similar, that's mostly due to behavior and not due to a super close relation. They have had plenty of time to develop different traits. And this is evidently one of those traits that has stayed different between these groups.
It's interesting because if this is, if this holds up for all gators and all crocs, it's a minor difference, but it's a fundamental difference in the shape of their bodies, which brings me back to the spiders question of are crocs and gators now capable of doing and adapting and evolving in different ways from each other?
Yeah, there's definitely mechanical suggestions. A longer humerus or femur suggests deeper muscle attachments that go further up the bone. So it would make sense with the galloping. They also noticed another weird trend. Like they didn't draw any direct conclusions from what this might mean for this group, but when you look at the slender snout crocodilians, they found a trend among this limb length that is weird and just continues to add to the weirdness of slender snout crocodilians. They found that on average they have longer femur and humerus bones, but overall shorter limbs.
Weird.
Yeah.
So they have tiny zoogopodia.
Yeah.
If I'm using that word correctly.
Yes. Someone here who knows the term goes,
someone's twitching at somebody's like, that's not what it's called. It's called the autopodium.
So
that's one of them. Autopodium is one of them. Metapodials are out there. I know where those are.
They have tiny xylophones.
They have
and
pseudopodia. It's not even a real podia.
Yes. I wasn't ready.
Couldn't even afford the real one.
Not even a real podia.
The cubic zirconium of podia.
Now there's a little bit. I'm moving on because I got it.
No, please do. That's too much.
There's a little bit of hesitation. Dr. Hutchinson does make the suggestion that the differences could be a loss of cartilage in certain museum specimens and a difference there.
Yeah, that's in the New York Times article specifically that we're referring to. They asked John Hutchinson.
Yes.
Who knows his stuff? Indeed. That's not a criticism to be taken lightly.
No, but he does say if this is legitimate, then the locomotion difference view has some major potential. So
very
interesting finding. Doesn't like break open the case on anything specifically or definitively, but it's an unusual difference that no one really expected to find.
Now, would you say that this would change how tall alligators and crocodiles are?
It's crocodiles definitely do seem to be more mobile. It's one of those things where that was actually my first thought when I read this, was like, maybe that's why crocodiles get around so much better than alligators. Alligators are like terrible at walking around. Like they just don't wanna.
Maybe.
With that minor bit of rambling, we close up the news and bring you to the main event.
Curtains. I gotta stop there. That's too much.
I know, right?
We're gonna get sued.
We should if anyone's ever listened to a DVD with the audio descriptors for blind people watching it, we can do that.
Chapter 2, main
discussion. 2 red curtains, pull aside.
Stage directions. Yes, absolutely. David and Will both take a drink of their water bottles, clear their throats, prepare. Now it's just NPR.
I was about to say that we're shifting into NPR.
That's NPR voice. There are 3 days left in our giveaway sweepstakes. For the next 3 days, if you donate any amount of money, an anonymous donor will double your donation. Ediacaran.
The Ediacaran Biota.
Let's talk about that.
All right, good suggestion. All right, well, I guess I can wing something.
Sam told me to talk about
it. The Ediacaran Biota is a weird chapter in Earth's history, mostly because of how little we truly know about it. As is a common theme, and we've mentioned it before, the farther you go back in the fossil record, the less resolution you get, and the harder it is to tease out details both of timing and organisms and form and function and all that stuff. This takes that whole experience to the next level and has so many open questions that it's a fascinating topic just because of the weirdness and the unknowns.
Yes.
The Ediacaran Biota refers to a group of organisms during the Ediacaran period, the period ending at the beginning of the Cambrian. It is the last period in the Proterozoic eon and Neoproterozoic era.
Yes, that is very important. If you remember when we talked about the geologic time and we did our geologic history thing, we mentioned that the Phanerozoic era is the era of modern life.
Yes.
The defining characteristic of the Phanerozoic eon, the Phanerozoic eon, is that the last 540-ish million years have had actual plants and animals.
This is before that.
The Ediacaran period is the very brief amount of time before the Phanerozoic started, where we had multicellular organisms in the fossil record.
Now, you'll notice that we're specifically using the term organism because we're going to get into that.
I almost said plants and animals, and I went, well,
jury's out on that. This is the Ediacaran period itself is a 635 to 543 million years ago. So not quite 100 million years. And as I said, ending of the Proterozoic eon, beginning of the Phanerozoic, butts right up against the very famous Cambrian, and it begins at the end of the Cryogenian period.
Yes.
Famous for 2 of the largest ice ages in Earth's history.
Yes, snowball Earth.
Yes. And so this plays into some of the other hypotheses and potential solutions for the whole situation with this biota. And we'll get into that in a little bit, but it's very important that we were coming out of that snowball Earth period.
Mm-hmm.
So coming out of a cold era into the Ediacaran, this is definitely warming up, and we're definitely seeing increases in stuff, even though things were not nearly the same as today when I say things were increasing, but there was increases in oxygen during this time. Still low compared to, later times, but there was an increase from previous. And otherwise you were looking at mostly oceans with those famous microbial mats all over the place.
Yeah, this was still a time where beneath your feet, in the water, because that's where all the life was, it was just mats of algae-like gooey stuff.
And that was the basis of living ecosystems at that time.
That was actually pretty much all of living ecosystems.
Exactly. Like this was what life was. Now, fun fact on the Ediacaran, and we'll go into a little bit more on like the changes we were seeing during this time that lead into the habitat that this biota occupied. This is something I didn't know until I was researching it. The Ediacaran was ratified as a geological period in 2004, making it the first geological period declared in 120 years.
That's very interesting.
Yeah.
I actually read about that a bit, hints of that it was sort of Ediacaran time period was, I think, used sort of colloquially for a while as the time that these weird organisms were around. And then eventually they said, well, we're going to make it official. This is an official geologic period. Because we don't typically talk about once again, go back to that history of the Earth, but we digress we did. We don't often talk about the really old eons at such a specific level, because we don't often have that kind of resolution so far back. So a lot of discussions of the really, really ancient stuff will go, and there were some errors in there, and then moving on to the Cambrian period, because now we can talk about very specific time frames.
Yeah, it's the same reason that as you go older, the periods and the eras get longer, and the closer and closer you come to modern day, they tend to get a little bit shorter as we are able to more accurately define things. Because back then it's like, well, I know that this 100, or 200 million years definitely has something similar in it. With the recent ones, we're like, oh yeah, this 20 million year range is definitely.
So the Ediacaran is a little bit special. It's got some unique stuff. Oh, and I should mention also, for anybody out there that has seen the word Ediacaran, Ediacaran, and wondered how to pronounce it, we are pronouncing it Ediacaran because I used to say Ediacaran, and then an Australian man scolded me.
Yes.
So my understanding is that Ediacaran is the correct pronunciation.
Yep. And we'll get into why the Australian man is the authority on that in just a moment.
So, because he was bigger than me.
Yes. Because their accent is better. I also called it the Ediacaran. Now the Ediacaran period.
That's Ediaccurate.
Yes.
Cut that out.
Yes. Edie, I don't care. Whoa. But
Edie actually.
One of the fun things I learned while looking at it actually had to do with, and we've mentioned this, but Earth's orbits and the orbits of planets in general do change over time. So orbits are slowing, they are distancing. Eventually, all orbiting bodies will float off into nothingness. But less depressing than that, back then, the moon was closer. So this meant that its orbit time was shorter, but also tides would have been more aggressive and quicker than today.
That makes sense.
Yeah, it's those little things you don't typically think about, but tides would have been very different back then.
Interesting. Yeah, we lose about 2.5 inches, I think, of our distance to the moon every year.
Yeah, and so it's enough to change. The days on Earth would have also been shorter, about 21 hours, so nothing ridiculous. It wasn't like a 2-hour day, but still shorter days. As I mentioned, microbial mats all over the ocean floor. Ice sheets were retreating at this time, so we're starting to see a slightly warmer environment, slightly more oxygen in the atmosphere. This is actually a interesting one because they also noticed a carbon isotopes decline in the rocks, and they think the oxygen and carbon change may be linked together.
Interesting.
One causing the other with their chemical reactions, and this definitely could lead into the effects on life. There was also an increase in tectonic activity. We saw a lot of changing around of the continents. At this time, there was a supercontinent, Rodinia, or Pangea 1. as some people nickname it sometimes,
That's
began.
weird.
Yeah, I know, right? It really should be like the Pangea prequel.
Yeah, what a insult to Rodinia. I am my own supercontinent.
Yeah. Have you heard of Pangea? Yes.
Yes, sir. We keep meeting.
Yes. It began to break up at this time. So regardless of how it felt, it's done. And it made a new supercontinent, the new supercontinent of Pannotia, centered on the South Pole, and still during the Ediacaran, at about 550 million years ago, just toward the end, Pannotia broke up into the continental blocks of Laurentia, Siberia, Baltica, and Gondwana.
Yeah, some familiar ones.
Yeah, a little more recognizable. So this was happening right at the end of the Ediacaran.
So the take home, I think, here is that the Ediacaran was a bit of a tumultuous time.
Yes,
There's a lot of change going on.
Mm-hmm. Lots of things changing, and some of it, hopefully, making things more fit for life.
Mm.
Now, the Ediacaran biota itself, the fossils that were found, we'll get into what they looked like in a second, but I wanted to talk a little bit about how they were discovered, because their discovery was very unique, because it was almost... They were discovered before they were identified, which is not unusual, but these were actually discovered before they were acknowledged as what they are.
Interesting.
Yeah.
Yeah.
So the first ever fossil from this time period, or from this biota, from this weird group in the Ediacaran, were disc-shaped fossils, imprints in stone, that were found in Newfoundland in 1868 by the geologist Alexander Murray.
Mm-hmm.
He found them useful for dating, but not much else was done with them at the time. So they were useful for identifying the rocks and biological dating, but they didn't make a big fuss at that moment.
Yeah.
In 1872, Elkanah Billings suggested that these were simple forms of life. So it took a few years before someone went, hey, this might be a thing. But basically, because it lay below the Cambrian strata, everyone just discounted it.
Interesting.
No one would acknowledge that there was life before the Cambrian, because at that time, the Cambrian was seen as the beginning of complex life.
It's also worth noting that this wouldn't have looked like what we were used to life in the fossil record looking like. Because you'll remember from our episode 9, Cambrian Explosion, we mentioned that one of the big innovations in the Cambrian was shells.
Yes.
And eventually bones and teeth and hard stuff.
Mm-hmm.
Like Will said, this is a disc-shaped stamp.
Yep.
In the sediment. This is a squishy thing.
Yeah. It literally looks like a very shallow cone pressed into the sand.
Yeah, and so for people back then looking for bones and teeth and shells, this wouldn't have looked like a living, like the fossil of a living creature.
Yeah, well, it'd be the same as if someone just came up and said, "Hey, I saw a T-Rex the other day." Your initial reaction, "No, you didn't."
I think you're wrong.
Yeah, I'm pretty sure you didn't. And that was basically what happened here, is that they said, well, no, because there wasn't complex life at that point. Mm-hmm. And it didn't shake things up once again. So it was interpreted instead as gas escape patterns in the sediment.
Inorganic feature.
Yes, it was a natural formed feature. Because once again, they didn't look like animals. They didn't have little arms or legs or anything like that.
Mm-hmm.
Way later, we're now in 1933. Similar specimens are found in Namibia. And this is by George Gurick. And they were initially misdated as Cambrian, since once again, if you found complex life, it must be Cambrian.
Mm-hmm.
And no actual links were made to the previous findings, but these were the first Ediacaran specimens identified as life.
Okay.
So now we're slowly getting there, but it took a while, and still they haven't recognized those other discs as being part of this same weird category.
Right.
Now we've jumped forward a little bit. 1946, Reg Sprigg, and this is where a lot of things start to stem from. Things start happening a little more quickly here. Discovers what is thought to be jellyfish fossils in the Ediacara Hills of Australia.
Ah.
Name drop.
Australia.
Where it would eventually lead to the naming. This is still believed to be Cambrian. And finally, in 1957, a frond-like fossil is found in England, correctly dated to the Precambrian. And now things kind of start to fall together. Just a couple of years after that, paleontologist Martin Glasner connects these more recent fossils to the earlier finds. And now the Ediacaran has not been named yet, but has been kind of identified as a period with complex life.
Right. We have it. We got it in Newfoundland and Namibia and England. We're seeing these weird things showing up right before the Cambrian. Absolutely.
And since then, they've been found on every single continent except Antarctica, yet, I suppose.
Yeah, it's only a matter of time, I'm sure.
Keep turning that thermometer up, and that thermostat up, and we will get to those fossils.
Yeah, big sigh.
Now, as I mentioned, they haven't gotten the name yet because they actually went through a number of names, and some of these names still float around every now and then for this era and biota. There's a few put forward. The Sinian was one of them, but the one that kind of still persists every now and then today is the Vindian.
Yeah, that's what I've heard.
Yeah, so you'll hear that pop up every now and then, but typically it's the Ediacaran, or the Ediacaran is sometimes like the.
I know an angry Australian man who'd like to have a word with you.
There's one that's what is it? It's the Ediacarian. That's the other one that every now and then they'll add. Basically, they add another I with the second A.
Like aluminium.
Yes. And so
crazy people in all the other countries.
Yep. Yes. Say it right. The Ediacarian is sometimes also used, but usually it's Ediacaran.
Yeah.
And now we finally have the age and the biota is recognized. Now, the reason they call it a biota is that it is not confirmed that these things are related or that they're the same kinds of things, but because they're all kind of equally weird, they've gotten put together. And we'll go over that grouping a little later on when we really try to talk about what they are.
Yeah.
But first I want to describe what they look like, because there's a wide variety of these fossils. They actually have a great bit of diversity in their shapes and forms. So this was a pretty rich time as far as weird early organisms go. So typically, these fossils, which are seemingly almost all soft-bodied, must be being either covered very quickly or in very soft sediment, or fossilized within the microbial mats.
Right.
Which is actually a big part of it, is many of these are often found in areas with microbial mat fossils in evidence. And this cemented sediment could either be keeping the impression or even covering the organism to preserve it. That and sandstone and ash bed fossils are the two most common, or the actual sediment and the microbial map are the two most common forms of fossilization for these weird things.
Yeah, you need very particular conditions to preserve soft-bodied organisms like
Absolutely. And people have pointed out that it seems like something was different. Something different was happening during the Ediacaran that allowed these very delicate organisms to be preserved as often as they were. So either the environment was just especially well set to allow it to happen, or there was some other quality that was affecting it. But it's a unusual amount of preservation for such, because many of them are not found in just Burgess Shale, ideal sites.
Right.
They're sometimes they're sometimes found in weirder or just less ideal fossilization sites. Now, there's a couple of morphotypes that you typically see. Once again, not necessarily families or classes or clades, but shapes that seem to kind of be able to be grouped together.
Yeah, morphotypes is a term that paleontologists will use when we've noticed that there is a difference in the shape of a few things, but we're not comfortable saying they're different species or family. It's just morphotypes just means shape.
Yeah.
We have 3 different groups of shapes. We have 5 different. These all are shaped the same. These are all shaped the same. We're not sure how to classify them. So for now, we're just the round ones, the square ones, the triangle ones, basically.
It's a type of morphology. That's basic. It's the slender snout crocodilians. There's a great one of those because there's different slender snout crocs from different groups, but it keeps showing up throughout their lineage. So we talk about the slender snouts because there's something there.
Yeah. When we did the snakes from the Gray Fossil site, before we started trying to identify species, we split them into morphotypes.
Yeah, absolutely.
We said, these all look like this. They group together, these group together. And then later we went in and started actually splitting them out.
Well, it's like when you sort a jigsaw puzzle. Find all the edge pieces, find the 4 corners, find the blue pieces, find the black pieces, find the red pieces.
Yeah, absolutely. Your morphotypes.
Then you start to go, all right, that's definitely got a part of the book in it. So put that with the table pieces. But it's the same idea. Here, these are very rough groups because some of these are still argued on definitely exactly what they are. The first are the quote-unquote embryos, because when they were initially found, they kind of resembled multicellular animal embryos. Mm-hmm. They are not thought to be actually embryos by most, but they do resemble it. Skeptics have suggested they could just be inorganic structures from minerals precipitating in holes that create this little rounded enclosed.
Yeah. Concretions, basically.
Concretions. They could be resting stages for adult forms, or they could be the adult form of a weird thing, or just large bacteria, though that doesn't really have a lot of support to it. The person who suggested it has not really that has not continued to find support since it's been suggested.
Right.
This one, the jury are still out, but they're definitely a feature of the Ediacaran. So they're there. The very famous, as we already mentioned, discs are a big part of this fossil assemblage. Only the underside is ever preserved, which leads a lot to think that this might be not actually the whole animal, but a mounting point.
Yeah, the stand.
Yeah, stand. Where
like if the Pixar lamp was hopping across the sediment.
Yes. They think it might, and it has kind of this dished bowl. Initially, it was thought to be jellyfish or some other cnidarian because of the round and slightly shallow shape, but doesn't. Since then, it's been basically confirmed that it doesn't share enough features to have any support for that. If it is a holdfast for some sort of stock organism, they think it might have been formed by it rotating in a circle and scraping out an area around it and creating this little cutout, basically, this little shallow crater. Yeah. It could be things like you're going to see this a lot for this episode. There's a lot of suggestions for a lot of these, and some of them are like, oh, that makes sense. They could be a holdfast or a giant protist.
Yeah,
basically a really big amoeba, and these still exist today. They're in the deep seas. Typically, you find them on like the abyssal plains, and they're basically just giant, very similar to amoebas that can get pretty large.
Interesting.
A good example of one of these is the Aspidella, and this is actually the first Ediacaran fossil ever to been found, even though it wasn't recognized as that. This was those initial discs. They range in size from 1 to 180 millimeters, so we're talking 18 centimeters in diameter for the very largest ones, but most are smaller than 10 millimeters, so pretty small.
Yeah,
these are not
super tiny.
These are not big. Very common in deep water sediments, which is what leads a lot. This kind of comes up with a bunch of them that if it is a holdfast organism of some sort, it is either kind of filter feeding or something because it's probably too deep to photosynthesize, which
like a crinoid.
Yes,
like sea lilies.
Exactly, and so that's one of the suggestions, but it could also be a giant single-celled organism. So some, as it was just described, bags, which look like mud-filled bags. So you got some that are very vague shapes that are just odd. One is these are interesting. The toroids, which are famous from Namibia, which effectively look like flattened rings. A toroid is that particle accelerator shape, that
the donut.
enclosed donut ring.
Yeah. It's the shape that sigil is.
Yes, exactly.
For the city of doors for you hyper nerds.
These little sigils. Oh man, there's a whole D&D conspiracy theory for how our Earth came to be and how life came to be. Those are a bunch of little. This is a little flattened circles basically, and the kind of thought is that maybe the center is the large gut cavity from a circular body. So the body would actually be flattened circularly, and the front and back, if there is one of those, would be on the edges of that circle. Yeah, those are very, very common in Namibia, which we'll get into because Namibia is one of the key locations for these fossils. Quilted fossils, which are probably some of the ones most well known, are the kind of, they have this pattern in them that looks described like an inflatable mattress, very much that ridged, concentric repeating pattern.
Yeah.
Frond like, think of like a feather pinned, quill sort of thing. They're often compared to sea pens, which is a type of cnidarian that is a stationary filter feeding organism today. Research has shown that they are not, but when you look at the pictures, they look a lot alike. So there's still kind of hesitant connections there. These get more interesting because we have now two groups within this, two more morphs, the rangeomorphs and the ornithomorphs. The rangeomorphs are interesting because they are the ones you often hear about or see pictures of, because they've got a central kind of spine or connector down the middle, and then these ridges, these fronds, branches coming off from it, very much like a fern.
Yeah, they look like a leaf, like a big, like the kind of leaf that a cartoon character would fan over the king.
Yes, like a big palm frond. And so, I mean, the frond gets used to describe these a lot. They seem to have a semi-rigid organic skeleton.
Mm-hmm.
Once again, they can be found on the seafloor, shallows to abyssal, so
interesting,
wide habitat variety, but bottom-dwelling, non-moving, sessile.
Yes, skeleton, by the way, like a mineral skeleton.
Yes, not like...
In case bones. People heard that and thought, not bones still.
Yeah.
This is like a coral skeleton or a sponge skeleton.
Yeah, that's a internal structure.
Yeah.
These are potentially asexual because we don't see any signs of reproduction or anything like that. There's also no direct sign of a gut or mouth. So
so we don't know much.
No, it could be filter feeding, or it could be getting nutrients through osmosis just straight into the body cavity, just directly from the water. The famous one that often gets described here is Chirina, which is the specimen that finally dated the biota to Precambrian. So this one often is very famous and will come up whenever you look up the Ediacaran, because it's often pictured, lots of artistic reconstructions of it, and it really put them on the time scale map. The ornithomorphs, or the ornithomorpha, are very similar, still got a very frond design to them, but they have, instead of being like a leaf where they're flat, they have multiple ridges coming off of the central spine.
Oh, so like in cardinal directions almost. Like a compass rose from the, like looking down on it, it'd be like a compass rose coming out in various directions.
They minimum had 3, but they could have up to 5 or 6, it seems. Because when they fall down and fossilize, typically only 2 of those sides get fossilized. So you don't always get to see the others, but it had a 3D, a 360 design instead of just 2D flat.
Interesting.
They're also their fronds are a little bit different. Each lobe is made out of parallel ribs and extending from that central axis, and on those ribs we have continuing little ones. 2 of the more notable ornithomorphs are the Swartpuntia and the Pteridinium. Once again, very similar design to what I was already describing, but the thing that really sets them apart as being weird is these have none of the signs, as I was mentioning, but no signs of a mouth, no signs of an anus, no signs of eyes, no signs of legs, no signs of antenna, no signs of any appendages or organs.
Yeah.
So, like, no signs of anything lifey related, at least
like
animal-wise.
A sponge, it sounds like.
Yeah, so it definitely could be something weird like that. These are typically actually in shallower sediments, so they may have been photosynthesizing.
Interesting.
So these could be living a very different lifestyle than our rangeomorphs. So still don't know. Now, those are most of the Ediacaran shapes that you tend to see, but there are some, and this is weird, non-Ediacaran fossils.
Cool.
And basically what that refers to is there are some fossils that show up during this time that do not appear to be within this weird group at all, that seem to have definite connections to other known life.
Interesting.
So there are some fossils that we see there that potentially could be more recognizable. Some of the more notable ones are early bilaterians, which is the group of life that we and many other animals are in.
Yeah, things that are like symmetrical side to side,
Yes.
like lobsters and humans and elephants and stuff.
Yeah, that are not like symmetrical around a central point, but instead a line down the middle.
Yes.
All that good stuff. You also start to see the beginning of the small shelly fossils that we mentioned in our Precambrian or our Cambrian Explosion episode. So these are those tiny, calciferous, hard body parts, the beginnings of what would eventually be exoskeletons and things like that.
Yeah.
These start to show up there. They'd be more numerous in the Cambrian, but we do start to see them. The most notable is the Claudidinae, which are these tube-like shells that, very interestingly, often show signs of what seem to be boring holes.
Oh.
Which is typically the result of predation.
Yeah, something was getting in there and sucking up the gooey stuff.
Yeah, so we see this from shells today. There are predatory snails with their radula that they use to drill through the shells of other organisms and eat them from the inside. So,
like a horror creature.
Like a movie monster of our nightmares. This was evidently happening back then, which at least suggests that there was already predation present during the Ediacaran.
Yeah.
So that's something that has to be taken into account when trying to figure out what all was going on. And then finally we have trace fossils. So we do get some leftovers. Right. There are some burrows. Not a lot of horizontal ones, though there have been some found more recently that at the very end of the Ediacaran that show a little more complex up and down burrowing, but most of them were horizontal. So like just on the surface or under the surface of the sediment, and or maybe even under the microbial mats and things like that. Like not deep, just underneath.
And that's one of the things, we mentioned this in the Cambrian Explosion episode, that's one of the big features of the Cambrian is that you start to see creatures really getting down into the sediment. And that's part of the substrate revolution. The microbial mats start to disappear as lots of animals start burrowing and digging and messing with the sediment, and it changes what the floor looked like.
Absolutely. It literally opens up new ecosystems and niches. So you see a little bit of this. Now, some of those simple horizontal burrows could actually just be created by things rolling around, basically moving around on the surface, not actively digging. But the fact that there are some vertical burrows show that you could have the beginnings of more complicated life. And if these burrows are legitimate, then that suggests organisms with a head, a front to be burrowing with.
Interesting.
Not all of that's valid because some of the burrows don't seem to, their shape doesn't really seem to support that they were, organized burrows by a living thing. But there's definitely some of that. And then we do get paths for certain organisms. So not digging it all, but just, pathways, not footprints. But we get Yorgia and Dickinsonia are two things that they kind of are like shield shaped. They're flat. They've got like a ridged disc, and they are, if when you glance at them, they're reminiscent of trilobites, and they're got a little rounded front section and kind of a almost tapered back or we assume front back section.
Mm-hmm.
They're like these little flattened discs, and they have been found with a pathway behind them. So there were some that were mobile.
Interesting.
Yeah, or definitely appear to be mobile.
So it seems like mixed in with those weird Ediacaran things are the early signs of the familiar Cambrian type stuff.
Yes.
Things that are moving, things that are burrowing, things with shells, just the very beginnings of those. And I think that one of the really big take-home points to notice about the Ediacaran stuff is that, you mentioned this before, that, sometimes you'll hear them called the Ediacaran fauna or the Ediacaran assemblage. And that's not necessarily accurate, because those are words that you normally use for a particular group of associated fossils. And the Ediacaran fossils are worldwide. They come in all different shapes and sizes. It's basically our word for all the stuff that we don't know what it is.
Yes, exactly.
And to listening to your descriptions of this, it really is that they're fairly simple shapes, fairly simple body plans, probably living pretty, simple and straightforward lifestyles.
Yes.
Things like we're comparing them to sponges and corals, where you have these are sort of the earliest experiments in complex, large and compared to microbes.
Absolutely.
Before this.
The biggest ones got to be 2 meters, so some of them were significant.
That's actually enormous for back then.
Some of them were, but most of them were pretty small.
But yeah, so and that makes it really difficult, right? You've got the combination of we're not getting many fossils. They're not fossilizing particularly well because they're soft body, because they're unusual shapes. They're hard to discern what's going on because they're very simple and because they're very unfamiliar. We can't look at them and say, that's an arthropod. That, you hear about Cambrian creatures and it's always like, well, Anomalocaris, we think we figured it out, what family it's in or what, groups it's related to. And there's lots of arguing back and forth, but at least we have a multiple choice. People are like, well, we're pretty sure it's either an arthropod or an annelid or this. The Ediacaran stuff's like, I don't even know if this is a plant. Or you mentioned protist or animal.
Yep.
This is at a time, and we've mentioned this before, when you start to see the earliest members of a group. We mentioned this with crocs, and we mentioned this with snakes. It is very hard to tell the difference between what will eventually give rise to different like telling gators from crocs is a lot harder 80 million years ago when they are barely split from each other.
Yep.
What we're talking about is a time period where that situation is happening with all multicellular complex organisms.
Yeah. With with the beginnings of complex life.
It's it's eukaryotes.
When you're starting to decide maybe more cells?
Yeah, like we don't have legs, we don't have eyes, we don't have teeth, we don't have mouths. And that makes it really difficult to sort these out. So like we said before, we're not grouping these taxonomically. We're not saying these are relatives, these are relatives. We're saying for the time being, these are the round ones, these are the frond-shaped ones, these are the little embryo ball things.
Yep.
We're trying to figure out what these were.
Because they have so many weird features, and they're lacking so many things that we would typically look for. The things that we would try to be identifying on them. And so far, still just haven't found anything. Now, to talk a little bit about that whole concept of the organization, there are some theme-ish things. We do have some assemblages. Now, not as in, organizing for what they all are, but there are areas where we find a trend in what kinds are found.
Okay.
And so there's three main assemblages. Now, the Ediacarans are known from 25 total localities, but the main assemblages are the Avalon type assemblage, the Ediacara type assemblage, and the Nama type assemblage. Each of these have slightly different features, and slightly different fossils are found, but there is kind of a trend of the fossils found in each area. This was at times thought to be maybe a evolutionary transition of between the locations, in that we were seeing the kind of different overall communities taking over from one another.
Okay.
Since then, because of the wide areas of these assemblages, and they seem to overlap in time, all three have been found in the White Sea region in Russia. So it seems like most likely this is representative of different environments than different evolutionary times.
Okay.
Now, each one has let's just go through them quickly to give you a kind of idea of what each one represents. The Avalon type, which was defined in Mistaken Point, Canada. I double-checked that to make sure.
Are you sure that's the name of the point?
I may be mistaken.
Hey-o.
It's the oldest of the localities, and easily dated to the ash beds that they have there through uranium lead dating. And it's typically deep sea dwelling rangeomorphs. So those frond ones again. The Ediacara type assemblage is based off of the Australia's Ediacara Hills, where they got their name from eventually. These fossils are typically preserved in rocks of coastal lagoons and rivers, and mostly it's imprints in microbial sediments, and some are in sandy sediments. So we're getting typical the specific kind of rock, but these are almost all in microbial beds, and so that mat again that's helping preserve the fossils. And then finally, the Nama type assemblage is from Namibia, as I mentioned, and we have cool ones here. 3-dimensional preservation in sandy beds is very typical of this area.
Interesting. Sounds like a good assemblage.
So this could represent burrowing creatures, or just that it's surface and getting buried very quickly to preserve the top. Often found in sections containing microbial mats again. And this is areas mostly interpreted as sandbars that would be formed at like the mouths of deltas, distributaries and stuff like that.
Right. At where rivers are meeting your seas.
Exactly. So we're still in the seas, but we have water flowing into it. And so those are the 3 main assemblages that are well known, but there are others outside of these, and not all of these are found in those locations. So
Right. Yeah, like we said, they're everywhere.
It's like the Burgess Shale style, or type fossilization sites.
Right. Those are the best ones.
Yeah, exactly. Now, as for the fauna, to go back to what we were talking about with how weird they are, there's a couple of hypotheses as to what they might actually be. So there are a couple of, hazarding guesses as to what they could potentially be. The first one is STEM group, that these could be the very beginnings of multicellular life that eventually somewhere give rise to one of the lineages that showed up in the Cambrian.
These were all. This was the extended family of the first plants, animals, etc. that we saw later on.
Exactly. So that they are somewhere connected to a modern phylum, and just unfamiliar due to having not yet evolved recognizable multicellular features. So, like we were saying, when they're new, they just don't have those things you're looking for. That is one of the thoughts. We haven't found any of what those connections would be yet. The most popular one is typically that they're Cnidarians. Once again, going back to that jellyfish connection, but in the sea pin connection. Cnidarians today are the most primitive of our multicellular relatives as far as animals go. And
depending on who you ask. Sometimes it's sponges. We actually brought that up in an episode recently.
This is true.
So, Cnidarians and sponges are constantly vying for the title of who is the most basal.
So they definitely have been connected. Most evidence nowadays, since time has gone on, goes against this. This has not really held up well over time. So
okay,
most likely not cnidarians, but that's still at least on the edge of the table. Protozoans, as I mentioned, protists are potentially a connection there. There are giant protists on the seafloor. Xenophyophores, as these are known, which are similar to large amoebas. They are unicellular, so a single-celled organism, but it's a big cell with multiple nucleus in it. So
interesting.
Multinucleate unicellular organism.
Protozoans also form kelp.
Yes.
So it's not too far-fetched necessarily to think that those fronds or things could be. I don't know, that might not be what they're thought to be, but
yes,
it's not unreasonable that a colony of protozoans could form a larger
absolutely
feature.
That they can form complex shapes that
yes,
that for most people recognize as plants. They look like plants.
Right.
The largest of these get up to 20 centimeters in diameter. So I mean, like, they can be sizable and have complex shapes. So potentially, this is another one. Most of these are very much one of those where it's like, yeah, I mean that doesn't just not make sense right away.
Could be.
Yeah, maybe put it on the bulletin board.
Yeah, we're trying to narrow it down.
This one's a little more interesting because it's kind of championed by Greg Ritalik, and it's the lichen hypothesis.
Oh, I like where this is going.
Yeah, so
that wasn't a pun.
The reason that this came up is many of the Ediacaran specimens are not completely flattened like we see many jellyfish fossils. They retain a little bit of their shape, so they're resisting whatever pressures are covering them during fossilization. The observation that Greg made was that the chitinous walls of lichen colonies could provide similar resistance to this compression.
Interesting.
Yeah. There is a slightly another connection there in that many of the specimens have been found in calcareous or gypsiferous, so calcium and gypsum sediments. And this is similar to the soils of well-drained temperate deserts, which is often climates that both lichenized and unlichenized fungi are found in. So this is fungus paired with a lichen and not paired with lichen, but you see similar environments for these organisms according to the sediments.
Interesting.
If that is where that connection is, but potentially.
As a brief side note for any listeners, if you're not familiar, so lichens, lichens are those mossy looking things you see on trees and logs a lot. But what a lichen actually is a symbiotic pairing of fungus and algae. So that's an interesting connection to be made. There are multiple species that are always found as a unit. An interesting comparison to make here.
Absolutely. Now, the next hypothesis is kind of the logical but definitely extreme solution in that they're a new phylum.
Right. That they don't belong, that they're a completely separate branch.
They are something that evolved and then went extinct, and then new things popped up.
And maybe they are many branches that went extinct.
Yeah, so that these could be a whole separate or multiple groups of complex life that was able to evolve, dominate, and then completely go extinct with no connection to modern day. Which is very extreme. But if this is true, it makes it very interesting because you'll often see it referred to as a evolutionary trial run for complex life.
Right.
It's like this was if that is what happened, if these are unrelated to the rest of today's multicellular life forms, this was another potential route that life could have traveled.
Yeah, it's interesting because that sort of idea comes in a little bit of a spectrum, right? It could be that some of them are branches off of the Cnidaria group or the sponge group, that these are closer to sponges, but they're a what we call, I hate this term, but I'll use it here, dead end lineage.
Yes.
Off the sponges, or a dead end lineage closely related to the jellyfish and things. Or the slightly more dramatic version that this is an entire group that is not closely related, that it is a branch off of all the things we have today.
Yep.
They're not the cousins of what we have today. They are a different trajectory, and all the stuff we're familiar with showed up on its own branch.
Yeah. So the new phylum is actually a very popular idea. You will see it pop up a lot when you read about the Ediacaran, because so far no connections have directly been found.
Right.
Now, there are lots of other suggestions that have been thrown out there. Those were kind of the more notable, but them being algae, them being fungi, them being slime molds, them being microbial colonies of some sort. Mm-hmm. One that I've seen popped up a couple of times that is just fun to say is that there's some kind of plant-animal hybrid.
What?
I've seen it pop up multiple times. Once again, these are things that have been just suggested. I mostly mention this to point out how far we're reaching and how far we're having to reach to try to answer this. Is people are like, I don't know, maybe it's both. It's
interesting.
You get some weird stuff. People are really trying to, it's throwing anything against the wall and seeing what might stick, because so far we don't have a good answer. Now, there is one recent discovery, discovered in 2014 in Australia. This is Dendrogramma. So this is a type of sphenophore, which is a colonial cnidarian, much like the Portuguese man of war. So cousins of jellies and corals and all that, but colonial organisms, so not a single animal. This was found very recently and initially could not be placed, but was more recently identified to be sphenophore. And some have made connections due to the oddness of it and similarity in appearance. It kind of looks like a little mushroom, but it has a very Ediacaran look to it. And so, once again, nothing hard. None of these are hard evidence, but there are little, very fine threads potentially connecting here and there, and we're trying to see which threads build up.
Oh, we're trying to go on what we know.
Yes.
And the trouble with this is that it's not something that we know. Or if it is, it's not. It's very different from that. And so we work with, best we can. We're trying to compare it to things that are in our experience.
It's that just made me think of a line from The Core where they're talking to the jerky scientist, and he says, "All science is best guess." And it's one of those where, like, it's a moment where they're making him a jerk, but it's like, well, I mean, he's not wrong though. Like, he's making a good point, but he's being a jerk.
Yeah.
I think of that all the time. Quickly, wanted to go over some of the observations and questions on their origins and extinction. And then we're gonna wrap this episode up with just a bit of discussion about why do they stand out in paleontology and our imaginations, and why are they significant. Their origin is not, of course, known. Otherwise, that would answer a lot of the other questions. The big question on it is actually the same, very similar to the Cambrian Explosion, of why then do we suddenly see multicellular life? Basically, the question of why did it take 4 billion years for complex life to develop, even though the first signs of cyanobacteria are 3.5 billion years ago?
Yeah.
So, like, why did it take so long? And there's kind of two main thoughts there. One is that it just takes that much time. That just the speed of evolution requires almost 4 billion years for enough complexities in the DNA or enough traits to build up to shift over to complex multicellular life.
Maybe.
That's a very similar to when we mentioned in Cambrian Explosion that perhaps we just got enough traits for that arms race to take off. And that's what caused the explosion in diversity. And so, that's come up with many things. Birds didn't take off until they had all the bird traits. So maybe it just takes that long to go from one cell to more cells. The other one is the other typical answer is that the conditions just weren't right yet. And that things on Earth lined up, allowing for life to get bigger and get, I don't want to say better, but get bigger and more complex and, potentially more exciting.
Right. just at the right amount of oxygen, the right amount, the right temperature, the right ocean conditions that
Exactly.
finally fell into place.
And those are all a big part. The oxygen one's an interesting one because, as is normal, passive oxygen transfer systems and animals requires higher oxygen in the atmosphere. If you're not going, then you have to just let it soak in. And so you need more oxygen to get bigger. Interesting thing here that's suggested is that one of the reasons we may have seen a rise in oxygen is that reactive elements like iron and uranium that would absorb atmospheric oxygen to effectively rust may have that's how much time it took for them to finish rusting and oxidizing.
Yeah, that they were those chemical reactions were going on until this point.
And now at this point, oxygen was finally able to build up and begin to promote life.
For more chatter about that, dear listeners, if you haven't already, go check out episode 9 because we talk for quite a bit about this question of why did it take so long for life to get to that point.
It's very, very common connections there. End of glaciation is another one that comes up for the Ediacaran. That maybe it was just too cold. Now, people have brought up issues with this one because they point out that the abundance of life beneath Antarctica waters might argue against glaciation pushing down life.
Right.
It has
now the counter argument to that, of course, what might be that you would say that all the life that's down there is descendant from life that has been successful for many millions of years. So
it's definitely one of those where there's not, but things have pointed out that the question of does cold water really slow down evolution is not actually a given.
Right.
So
right.
There's lots of questions there. The extinction is once again very similar to what we've said, but this one has some specifics due to that it butts up against the Cambrian Explosion.
Mm-hmm.
The first one that people point out is preservation bias. Absolutely is a factor you have to acknowledge. Like we were saying with the pterosaurs, the Ediacaran Biota could have continued further along, but as I mentioned with the fossilization, whatever special conditions it was that allowed them to fossilize so well during the Ediacaran may have ended.
Right. So this is an interesting inverse to the normal preservation bias question at this time period, because in the Cambrian Explosion episode we talked about how the quote explosion might have been more gradual. We just weren't seeing the creatures fossilizing earlier very often. In this case, you're suggesting, as others have suggested, that it might be that these Ediacaran creatures didn't all disappear at the end of the Ediacaran period, but much like our pterosaurs in that news article, may have continued for a while. We just weren't seeing them because they weren't being preserved very much.
Yes. And one of the big potential supports for this is that some Ediacaran-like organisms or fossils have been found in Burgess Shale type fossil deposits. So there have been some
interesting
things that have popped up in the Cambrian that sure seem to be evidence that not all of the Ediacaran biota disappeared right at the Cambrian.
And there's probably a good chance that a little bit of both is true.
Exactly.
That we're seeing a little bit of the Cambrian bleeding earlier and a little bit of the Ediacaran bleeding later, and that boundary isn't a hard line.
Mm-hmm. Of course, as is with all extinctions, change in environment is definitely a culprit.
Mm-hmm.
That's definitely something that we have to take into consideration. A lot of things changed during the Cambrian. We saw rising sea levels. We saw a nutrient crisis during that shift. Mm-hmm. There was lots of atmospheric changes. The oxygen and carbon dioxide levels were fluctuating, and the ocean chemistry started to promote biomineralization, aka exoskeletons. So big change there. So that could have been enough just to not be conducive to their lives anymore. The two that are more directly connected with the Cambrian explosion are predation/grazers and direct competition.
Yeah, other stuff moved in.
Yes, the predation and grazers is interesting because the predation is that maybe these other organisms showed up and started eating the Ediacaran biota directly and started to push them out of their niches, or that grazers came in and started to eat the microbial mat, which the Ediacaran biota depended on, and basically by eating destroyed their ecosystem.
And that's something, and I've said this before, that the way you cause an extinction, a mass extinction, is you mess up the ecosystem. However you do it, right? You pull the rug out from under the ecosystem. So as much fun as it is to imagine that Anomalocarids evolved and ate all the Ediacaran frond creatures, which could very well be partially true, the fact that when we get to the Cambrian, burrowers start changing up the sediment and animals, proper Cambrian animals, start eating those microbial mats. And that's where the Ediacaran creatures lived.
Yep.
That's their home. That's their foundation, literally. So that's always the first one that comes to my mind. I am not an Ediacaran researcher, but that for me that's the one that's like, yeah, they had the literal rug pulled out from under them.
Yeah, that's what pops to the forefront of your mind as soon as you think about it. Is, I mean, if I drink your milkshake, then you have nowhere else to go.
Yeah.
Now, the other option, of course, is direct competition, that they started getting out-competed by similar but more updated organisms that they were just not able to keep up with.
Right, especially in a changing environment.
Yeah.
That it's the update in that case is that we can get the same food that you can. We've also adapted quicker to the oxygen levels, the sea levels, the nutrient availability, the microbe, all that stuff.
Yeah, or we developed a new tool that gives us a whole new angle to come at that you just can't fight against.
Yes, remember from episode 9, the Cambrian is when creatures invented eyes and mouths and stuff.
Yep. So it's when the first Cambrian organism came up to an Ediacaran organism and said, "Hey, look here," and he goes, "Do what?"
Yeah. And he was like, "You're going to get out of our environment." He was like, "Bite me," and they were like, "Well,
well, you asked for it
if you insist."
So there's a lot of weird stuff with this. This is a fascinating group, a weird group, but they definitely stand out. And just, wanted to leave a little at the ends for us to just kind of discuss why that is. And the first thing I want to spark it off with is there's a paper that I will link in the blog post that asks the question, is there actually an Ediacaran biota?
Right.
Basically saying that so far we've yet to draw lines to any of these organisms. And that was a term that was used, but nowadays it is, the author suggests, an archaic term that really isn't valid other than talking about the time period.
Right, the stuff that lived at this time.
Yes, the stuff from, because there's a great quote, and this is, I alluded to it earlier, but the author says, "What differentiates a non-Ediacaran Ediacaran and an Ediacaran from a Ediacaran non-Ediacaran?"
Yeah, that about sums up the Ediacaran conversations.
Yeah, it's I find it fascinating. I'm always interested whenever we have large questions due to how different things were, because it's easy to picture that, the more things change, the more they stay the same, but sometimes no. Sometimes they were weird. Yeah. And I find that fascinating.
I think the Ediacaran is a really interesting time period to talk about, because basically it's got all the intrigue of the Cambrian, the early Cambrian, and then some.
Yes.
It's this time, it's this, all those questions of, why did life appear? Yeah, why did it appear at this, why did it become this way at this time? And what are all these weird things? Like the Cambrian is so fun because we're like, all right, well, we've got arthropods and we've got early chordates and we've got this and that. But then there's this weird stuff like Anomalocaris and Wawaxia, and we don't know what this is. And then you go to the Ediacaran, it's like, do you see anything familiar? Because I'm looking and it's just all very strange, which makes perfect sense. It's obvious, like, intuitively, of course that would happen.
Yep.
Of course you would have a very early time where everything is squishy and we have no good idea what's going on. That's a little exaggerated, and I don't want to insult the people who actually do work very hard on figuring this stuff out. But yeah, it's very mysterious group. And the thing that has come to my mind as we're talking about this I always think about the Ediacaran as sort of the Precambrian footnote.
Yeah.
Right? It was this short period of time where a bunch of weird stuff was around for a little bit, and then the Cambrian took over and, stuff got started for real.
Mm-hmm.
But the Ediacaran period, as you said, almost 100 million years.
Mm-hmm.
Which means that the Ediacaran biota was around for longer than primates have been around.
Yeah, yeah.
For longer than alligators have been around. Like, this wasn't a tiny blip.
Mm-hmm.
We don't know very much about it, which makes it seem like, as we always say, it's in the distant past. We don't know very much about it. But this was a significant chunk of time,
yeah,
during which whatever these things were, they were in charge. This was what global ecosystems looked like, and anything we learn about those is super fascinating.
Absolutely. And when it revealed itself in such an interesting way in time to me, because whilst we were looking at the Cambrian trying to figure out why are things happening now, why are they getting complex here, why is this the beginning, and all of a sudden we realize we're not even at the starting line.
Yes.
Like, oh, well, now why both? It's and
yeah.
We mentioned this with Darwin, but Darwin pointed out that to another quote, the difficulty of assigning any good reason for the absence of vast piles of strata rich in fossils beneath the Cambrian system is very great.
Yes.
And then we find that, yes, there was, but now it's really reveals more questions than it fills in, and they're big questions.
Yes, they are.
It's a cool thing because it opened a chapter before where we thought there were any more chapters, like before chapter 1, and
the prologue.
Yeah, and is just completely out of left field, just completely new and weird.
And I think as we continue to study it, decades from now, it probably will be less weird.
Yes.
And I think that we'll have a better idea of what it is. And I also think that, molecular clocks put the earliest plants, animals, and fungi at quite a bit earlier than this.
Yes.
So it's very likely that we will find the next iteration of this. Where it's like, all right, we have a general idea what's going on in the Ediacaran, but what the heck is this thing?
Yep.
From 900 million years ago. So, we're always filling in slowly the distant, the tapering ends of the origination and extinction are always hard to pin down because they taper in diversity and disparity.
It's like when we were filling in the world map during the age of sailing, and the Americas were unknown, and the size of the Pacific and Atlantic were not known. And as you explore more, you slowly go, oh, there's a whole continent here? 2 of them, you say. It's that kind of stuff where at some point we could absolutely find that, oh, yeah, no, this was going on for a long time. The reason it took so long is because it didn't.
Yes.
And so, yeah, it's an exciting thing. At this point, though, we are going to wrap up this conversation. This is, as usual, a very dense topic, mostly due to the amount of questions and potential suggestions and hypotheses that surround it.
Yeah, this was an episode of more question marks than exclamation points.
Yes. And so there'll be tons of cool links in the blog. So feel free to take a look at that if you'd like to delve more into this. And let us know if you have any comments or questions about this subject. And to do that, as usual, you can contact us on all of our social media sites. We have Facebook, Twitter. You can email us, commonascentpodcast@gmail.com. If you would like to go to Patreon and connect with us and comment on us there, we would love to hear from you.
Yes, thanks again to our newest patrons.
Yes.
Thanks again to Sam for making this suggestion. And another reminder that to check out our social media for the survey that is out there. If you like what you hear, let us know. If you don't like what you hear, let us know. Be gentle, but let us know.
Yes.
In the survey. And then eventually we will start putting the survey results together into action for the podcast.
Yes.
Check it out on the blog posts. Check out all that stuff. We release new episodes every fortnight.
Mm-hmm.
So keep an eye out in April for episode 32 of the Common Descent podcast.
Thanks again for listening, everyone. Hope you enjoyed a weird conversation about weird organisms.
From weird people.
Yeah, from the weirdest of those three. See you next time, or talk at you next time.
Bye.
See you, everybody.
Thanks for listening to the Common Descent podcast. You can follow us on Facebook, Twitter, YouTube, and check our WordPress blog for pictures and links after each episode. Huge thanks to our patrons whose support helps keep this podcast running and who get access to bonus goodies on Patreon. The song you're hearing is called On the Origin of Species by Protodome, which we found at ocremix.org. Thanks again for listening. We hope you'll join us next time.